But the share button is not working. It giving me the information only meeting organizers and presenters can share. So you have to add me as a presenter.
Yes, madam. One minute, madam.
Yeah, but I cannot share still.
Yes.
Yeah, now it came. So share. Can you see my slides? Can you see my slides? It's visible. I cannot hear anything.
It's visible, madam.
Visible?
Yes,
okay.
Yes, madam.
Okay.
Your voice, everything clear, madam.
It's not in the presentation mode, but its slides are visible, no?
Yes, madam. Everything visible.
Okay. So let me start the presentation. Actually, it's okay. May I start?
Karen, madam.
Okay. So the presentation title is Optimal Feature Subset Selection Algorithms Using Quantum-Inspired Machine Learning Tools. Actually, before going to that presentation, I assume that the attendees here have some knowledge about feature subset selection. If you have anyone have do not know this, but if this field, just raise your hand and ask me, or you can just ask me. Is it okay? Okay, let me then go on to my lectures. That this lecture actually is related to feature subset selection. The feature subset selection problem is an important prerequisite of any sort of pattern recognition, machine learning, data mining, and these types of algorithms. But why do you need feature subset selection? Before going into explaining this, as these lectures are going on the area of artificial intelligence, pattern recognition, and this area related areas, I would like to say a few words about this area. Actually, artificial intelligence, the area has developed from 1956, the term coined in Dartmouth Conference in 1956. But after that, this artificial intelligence has lots of waves. No? Sometimes it was boom, sometimes it went backwards, and now it's again a boom in artificial intelligence. The definition of artificial intelligence is very controversial. What is intelligence? That's a question. And how artificial intelligence can be achieved? That's another question. But the thing is that human being, from the very beginning of civilization, human being tries to use some machine to help them do their work. And from the birth of computer, ever since the computer was born, people are trying to use computer to help in their work. So basically, as the computer's powers gradually increased, in the beginning, computers were used only for computation, for high-speed computation, or what human can do in a minute, computer can do in a second. So actually, for the speed increase of computation, computers were used. But as the computer's powers are increasing and increasing due to the development of actually computer hardware, so the people are trying to use it in different types of problems, different types of applications are gradually developed, and people are trying to do something which people are good at. So those things are people are trying to use computers to do not instead of them, just to help them and assessing quickly. So this is the motivation nowadays for the this rapid development of this field, artificial intelligence field, for using computers, and this machine learning also has now grown so much. Now, actually, machine learning, when it was born or when the concepts were developed, that was in fact statistical learning. It's a field of statistical learning that now came into machine learning because those algorithms that are used in computers. So with the increasing power of computers, those algorithms are now implemented, can become useful implementation. So they are implemented to solve some real world problems. But many people actually in internet also, there are some articles, and many people tell machine learning is different from programming. But actually that is not. Machine learning, the definition in 1955, some people told that if machines can do everything, if machines can learn by themselves, that will be better. But the thing is that that is a metaphor. Machine cannot learn by themselves. Actually, what is happening that people are now trying to develop some algorithms. And you know from computation science that anything that you can compute, anything that is solvable must have a definite algorithm. So if you do not have a definite algorithm for a problem, you cannot solve the problem. So machine learning, what is machine learning? In my view, is a bunch of algorithms that are designed to extract the pattern from data. From large number of data, it extracts the pattern and solve the problem by extracting those patterns, recognize the pattern or classify the patterns, or predict the future patterns from the previous patterns. So these are a bunch of algorithms, and that are implemented in computers by definitely some programming. So programs are needed. So these programs implement those machine learning algorithms. Those are the bunch of algorithms. They implement these in computer. For implementation, we need the program, and this bunch of algorithms are called machine learning, and these algorithms are used in applications and real-world applications to solve the problems. Now people are interested in deep learning. So you can ask that what is feature subset, feature selection? So basically the features are when we analyze any data for recognition, classification, or clustering, or prediction, regression. So we need to classify the patterns, no? We need to group the patterns. So based on what? We express the data in terms of some features. Suppose when we classify some faces or recognize some faces, we do not know what we see, but we human being can recognize the face. But for computers to recognize the faces, they have to give some particular type of features of the face to recognize. Or if you have some data has some dimensions, we call that is a vector data. If you represent the numerical data to a computer, that numerical data is actually a vector of some dimension. So those dimensions we call feature. So if the data is high dimensional, for classification, if we do not need those too many dimensions, we remove some of the dimension, we remove some of the information from the data, so that it is classifiable in lower computation, with lower computation cost. So that is one of the objective, that we have to minimize the data dimension, that is the feature in one hand, and in the other hand, we have to retain those features that are very much dependent, that is very much necessary for discrimination of different classes, or very much necessary for recognizing some particular pattern. Now, in the era of deep learning, people may ask that why should we extract the features before, because we can give the raw data to the deep neural network, and deep neural network just classify it. But the problem is that deep neural networks are not the solutions for all problems. They are really a very good thing, and in some practical areas they give very good classification accuracy, and we can solve problems very efficiently by a deep neural network. But the problem is there are different types of problem. Just now I told about face recognition. When you recognize a face, somehow you recognize by some of the features of the face, but you don't need to know that. If your objective is to recognize the face, or just your objective is to recognize a picture, whether it is a picture is a cat or a dog, you just want to know that whether it is a cat or whether it's a dog. Why it is a cat or why it is a dog, you don't need to know. In those cases, we don't need to explicitly put the features out. We just give the image to the network, and network will classify it as either cats or cat or dog. But if the data is a medical data, if the data is weather data, or in case of medical data, if you have an image and or even if you don't have an image, you have some numerical data for some disease. So you have to classify whether the disease is a COVID or this influenza. So there are some factors, some features which doctors would find to say that the reason of that classification. They want to know the reason of the classification, which factor is responsible for being classified the disease as COVID or being classified the disease as influenza or whatever be it. So what is the factor which is working on that? That is feature to class correlation. That is very important. So in those cases, you need to know the explicit feature. So the problem of deep neural network there is deep neural network acts as a black box. So you do not know which is the cause of what. In some areas that doesn't matter, but in many areas that matters, where we want to know which is responsible for the classification, which factor, which feature is responsible for the classification, and why we classify the disease as this particular disease. So the inner knowledge, we want to know the explanation or the explanation for this classification or clustering or whatever be the problem. So in those cases, we need the explicit feature values or explicit feature which is important. And deep neural network has another problem also, that though it actually classifies from the raw data, it needs a lot of samples for training. In many practical problems, we don't have that many data. So in that case, before putting the classification problem into deep neural network, before that, if we handcraft the feature, select the features and reduce the problem in a lower dimension, that would be better handled by deep neural network. So this need of feature subset selection is there and will be there for any short pattern recognition, classification, or problems. Now, just now I told that feature subset selection is you have a lot of features for a particular problem. You need to select the optimum subset of the features. Optimum in the sense that it will give you lower computational cost, but higher classification accuracy. The number of the features should be as low as possible, and the selected feature should be stable. Now, in this particular talk, we have done a lot of work on this feature selection. My area of expertise is on feature selection, and we did a lot of work. But here, today's talk, I would like to tell some of our own work in this area using meta-heuristics and quantum computing. I'll show you the next slide. Is it visible? So basically, I told that things previously, that selection of the relevant features is called the feature subset selection. So all features are not important. We want to remove the redundant features, the irrelevant features, and we have to keep only the reliable features which are responsible for classification or regression work. And this particular problem is called the optimum feature subset selection problem. And as I told you, there are a lot of algorithms developed in this area because this area is quite old area. So mostly the feature subset selection algorithms are divided into three groups: filtered algorithms, wrapper algorithms, embedded algorithms. Filtered algorithms actually use basically for feature subset selection, we need to do two things. One is that you for a feature to be a good feature to be selected, the feature should be evaluated. So we need some evaluation metrics, and in the second stage we need to find out the combination of the features, that is the feature subset. So we need some search process to find out the best subset of features. So depending on these two processes, some of the feature selection methods only do the feature evaluation part and they rank the features, which is called this feature ranking. So they rank the features and they take the upper ranked features, and that's all. But the feature subset selection depends on the second step also, whether we use the search process to find out the optimum feature subset, because the main problem is that if you do only the feature ranking according to some feature evaluation criteria, the number one feature and the number two feature, the problem is when you rank them individually, they may come out to the number one and number two. But when you combine the number one feature and number two feature, that might not be the best feature subset of two features. So this was actually this was found by some person, Coward and Hart, in 1977. And for this, actually, you have to check all the feature subsets. So which one will be the best one for that? And that's why we need a search process to find out the optimum feature subset. Now, while we search this optimal feature subset, if we use the classification accuracy as the fitness function, those are the wrapper algorithms. But if we use the original evaluation metrics of the features as the fitness function, these are the filter approaches. And there are some hybrid approaches which uses both these methods. These are called embedded approaches. Now, for search strategy also for finding out the optimum feature subset selection, as this finding out the optimum subset selection actually is an optimization problem, combinatorial optimization problem. When the number of features are not many, you can just manually search all the possible combinations of features to make the subset, and you can evaluate them. But if the number of features is large, there will be a large number of possible combinations, and then you have to use an efficient search process. So there are many types of search process, complete search, heuristic search, and some meta-heuristic search. Today's lecture, I will tell you about some of our work on this feature subset selection problem using this meta-heuristics and some concepts from quantum computing. So is there any question? If at any stage you have any question, just ask me. So our main objective of finding out the optimum feature subset is to find a feature subset which we will tell the best feature subset or good feature subset if the classification accuracy using that particular feature subset is the highest, number of features is as low as possible, computational time will be low, and there is a stability in the, because stability means if we use one part of the data, that is the feature subset selected, and if we use a different sample portion of the data for the same problem, the selected feature subset should be same. But if the algorithm selects different types of feature subset for different parts of the data, that algorithm is not called a stable algorithm. So we need to design a stable algorithm which will produce a number of features as small as possible, classification accuracy as high as possible, and computational time as low as possible. So with this objective, we try to design some algorithms using meta-heuristic and quantum computing and quantum inspired strategies. We simulated our algorithms on different types of data sets with number of features from very low to quite high. So let me now explain our research. This work actually was done by my student, a PhD student. He did PhD under my supervision, Ashish, who is now in Bangladesh, and is a teacher in a university in Bangladesh. So I'll use some of the slides from his PhD thesis. So we used actually a particular meta heuristic, which is called owl search algorithm. That was not devised by us, but it was in the literature. That was a meta heuristic algorithm used for optimization problems. But that algorithm was never used in feature subset selection problem. So we picked up that algorithm and we converted it to binary form, binary owl search algorithm, to use it for our problem, feature selection problem with different transfer functions. Then we modified the algorithm a bit and named it MBOSA. And then we used some element or some concepts from quantum computing. Why we used, I will tell you. And then we devised two algorithms. One is filter based and one is wrapper based, where we used some idea from quantum computing. And finally, we tried to devise a quantum algorithm, quantum feature selection algorithm, which can be computable on quantum computer platform. But as we don't have any quantum computer now, we actually simulated in simulation platform, and we found that if quantum computer is available, then we could have a better algorithm. Anyway, I'll try to explain these algorithms a little bit in today's talk. So to start with, we initially started with this owl search algorithm. So owl search algorithm is actually a meta heuristic algorithm, and like these groups of algorithms, starting from genetic algorithm or particle soul optimization, all these sorts of algorithms actually use some sort of biological or social or some of the rules they use for searching process. So this one such algorithm is also a population-based meta-heuristic algorithm. This algorithm uses the owl's specific property of deciphering some or locating some prey in the night, also that without seeing they locate the prey by the virtue of their typical characteristics, that the sound come to their left ear and right ear, and there is a difference between the sound, and from the difference between the intensity of the sound, they calculate the distance of the prey from them, and they go near to the prey. So this auditory map of prey sound generated by this owl's brain, that owl's brain generates the difference between the sound, intensity of sound in the left ear and right ear, which come from the prey. So from the we use that particular property in this we use actually in our search algorithm, they use this particular property to develop the optimization algorithm. So basically what they did is that initially they initialized the some points which are the owls. Actually these are the possible solutions, and that in like any sort of this combinatorial meta-heuristic algorithms, they first generate a population. So here the populations are called the population of owls. So those owls are nothing but some points in a continuous d-dimensional space, and they generate it with a uniform random number. So those positions of the owl are the initial population of solutions. And the fitness value of the owl is defined by this equation 2, which is actually depend on the intensity difference of the owl's intensity difference of the owl's 2 ears of the sound which come from the prey. And actually I transformed this from a PDF file, and the equations are a bit distorted. Anyway, that distance is R is the distance from the prey to the owl. So the intensity is inversely proportional to the distance. So from the intensity, they assess the distance between the prey and themselves. So they try to move to the prey. So they update their position by the prey is also moving. So depending on the prey's movement, they update their position to be near to the prey, depending on the intensity of the difference of intensity in their airs. And there's a parameter eta, which is user-defined parameter. Like any sort of this type of algorithms, this parameter actually initially it is put at a bigger value, and finally it is reduced. The idea is that initially the movement should be high, because initially the search space we jump to the different points of the search space, but finally we have to move in a very short. When we find somewhat we are near the minima, optima, then we will move a little bit, so eta value will be gradually reduced. Like in GA also, this type of parameters we use, and we change the parameters from its initial value to final value. So here this owl search algorithm, one good thing is that like the most commonly used meta heuristic is genetic algorithm or particle swarm optimization. Most of the algorithms we have a lot of parameters, user defined parameters, but in owl search algorithm, only eta is the only parameter which user has to define. So this algorithm is quite simple. So we choose this algorithm for our experiment, and this is actually the flowchart of the owl search algorithm. Initially, you initialize the population of owls and the user-defined parameter, the theta, calculate the fitness value of owls, find the best and worst owl and prey, and then you change the eta value. Again, you calculate the difference in intensity, and then you update the position of the owls, and in the new position you calculate the fitness, and you do it repeatedly until you find your best solution, depending on your stopping criteria. So we use this algorithm to use for our feature subset selection problem. But feature subset selection problem is actually we need a binary space, because we use a string for features, which the 0 indicates that that feature is not used, and 1 indicates the feature is used. So the continuous OSA, we converted it to a binary variation of this owl search algorithm, and use some transfer functions for this mapping. So while we update the positions value is continuous, but we use some transformation function to transform it to a binary value, because our owls is in a binary space, a binary d-dimensional space. So we initialize the owls in, and if it's 0 means the owl is not there, and 1 means the owl is there, that feature is there. So in that dimension is used, or 0 is not, that dimension is not used. So accordingly, we modified the updating values of updating equations also, and we used the eta. Actually, we changed this eta into this equation where t is the total number of iteration, t is the current number of iteration, and rho v is a constant, which is 2.0. We just modified eta in this equation and use this equation just to that it matches with our problems. And in case of distance function, original owl search algorithm uses Euclidean distance, but in our binary owl search, we used Hamming distance as we use the binary space. So we use the Hamming distance for calculating the distance between the owl and prey. We use different types of transformation functions, transfer functions we call it, for V-shaped, for S-shaped, U-shaped, different types of this type of function, V-shaped, U-shaped, and S-shaped function with different parameter values. And we did experiment, and we use this binary owl search algorithm for feature subset selection problem in a wrapper environment where we actually selected the subset and then evaluated that subset evaluation we used by classification accuracy, and not only the classification accuracy but the number of selected features also. So in case our fitness function in binary owl search algorithm was developed by this equation 12, and one part is the accuracy, classification accuracy, and other part depends on the number of features, that the ratio of the features which are retained. So this W is a weight parameter. If we put greater weight for the classification accuracy, we put W value high. And if we put, we actually put greater value for the classification accuracy. It was around 9.8 to 0.9 we experimented, and 0.2 to 0.1 was the number of selected feature. We used some of the data sets from UCI depository, and we also compared our result with contemporary these meta-heuristic based algorithms, binary particle swarm algorithm or binary genetic algorithm. These are the data sets we used, 20 data sets. So this is the result for our different types of transfer functions, and we found that this Q3 function, we named it difference S1, S2, S3, S4 up to Q3. This function gave us the best result. So from now on, we used actually this function only, and this is a this is the result of this average classification accuracy using this, the best one, BOSA Q3, with other methods, which we compared with GA, PSO, and harmonic search for the different data sets. And we found that our developed algorithm is quite good compared to the other algorithms. This result shows the feature selection rate. So we found that in our algorithm, this BOSA, less number of features are selected, which can give the more or less same types of accuracy, which was selected by the other algorithms. So number of feature less number of feature with the same level of accuracy is actually a good thing, because if the number of features is less, then for classification, it will take lesser time. So this is actually, as we published the paper in these two publication. So for publishing paper, we have to do some statistical tests. So we did also statistical tests, which gives us that our algorithm is quite better than the others. So later we modified this algorithm, this binary owl search algorithm, by introducing three things. One is we introduced a self-adaptive strategy for parameter tuning that we call that this eta value, the only user-defined parameter. It was changed automatically, and depending on how the algorithm progresses, depending on the position of the optimum position, actually, and if it is stuck in some position, it's automatically it is moving from the stuck position. How it can move from that is a adaptive strategy we used for parameter tuning. And we use elitism and a mutation. Originally in OSA algorithm, there was no provision for mutation, but like in GA, we use some mutation operation also. That is changing some of the bits occasionally, making some perturbation occasionally in the search process. So we introduced these three things with this BOSA and named it modified BOSA algorithm. And again, we simulated this algorithm on UCI datasets and some of the high-dimensional datasets also. Here, we use decision tree with Gini index for the fitness function, because in BOSA, we used KNN classifier, but here we use this. And for final classification evaluation, we use that support vector machine. So here, our eta was converted, update with time like this. With this equation, actually this A, depending on this A value, depending on the problem, actually, the number of iterations needed are different. And depending on the number of iteration, how we will change our eta, that is defined by this equation. Because I told you that at the beginning, eta will be high, because at the beginning, our updation will be more, because it will be it can search the different spaces of the search space. So, but finally we have to move a little bit, like gradient search type of things. So eta should be lowered. So, but how we lower that after what iteration and what rate, that is defined by this equation, and that is automatically defined according to the problem. So this is one, and elitism means we just selected the best individuals, and we time to time we with some probability we did some perturbation by introducing this mutation. With this three things introduced in the BOS algorithm, this is the actually the algorithm chart. We got better results. So here you can see that for the data sets, our BOSA and finally the modified MBOSA, it produces better results in most of the cases. And of course, in compared to the other methods also, this method was better. This is a average classification accuracy, and for the average over all the data sets, and this is the how much the feature was reduced, number of features reduced, the feature selection ratio we called it. That is the initial feature by the final feature by initial feature. There's a ratio of the features that we retained. In case of MBSO, that is also less. So with less feature, higher accuracy, it's actually what we want to do, and we got it. So up to this, we use the traditional machine learning algorithms and feature subset selection mechanism in meta heuristics, but then we added some of the concepts from quantum computing. So why we added quantum computing is that for we tried this MBSA for this large number of high dimensional features, high dimensional data sets. So when you use high dimensional data sets, it takes a lot of time, and especially optimization problem in high dimension, it takes a lot of time. So quantum computing is better in optimization problem, taking lesser time. The main point where we focus on quantum computing is that in quantum computing, in classical computing, we have a two-state, you have 0, 1, but in classic quantum computing, it's represented by 1-bit qubit. So for 8 states in 3 qubit can represent. So the representation in terms of quantum computing, you can represent a higher number of bits in a lesser number of qubits in quantum computing, and that produces that we can search parallelly. That's why it produces lesser time in searching. So if you can use a quantum computer, so this is the sales point of quantum computing, and now people are actually using this concept of quantum computing in different types of machine learning algorithm, and the field of this quantum machine learning is gradually developing. So we also tried this concept of this optimization quantum in to integrate this concept with our meta heuristic to develop faster algorithms. So the main three concepts of this quantum computing is superposition, because here, as I told you, that 0, 1 is not two different state, it is in one state. So a qubit can be in 0 or 1 state together. And this is called superposition and entanglement. But when we measure it, collapses to one state. So all the calculation is done in limited time, but finally we get the result in the classical region. So this concept we used. How we used it is, we named it at quantum inspired OCA. So where we represent each feature by a qubit. And this initialization and then measurement and then fitness function calculation, which is in the process of this feature subset selection by any sort of meta heuristic algorithm like our modified BOSA. We have steps of initialization, and then you have the step of updation, and then you have to calculate the fitness function. So for all these steps, we used quantum implementation, and quantum implementations are actually done by some of the gates in there. So we used Hadamard gate, rotation gate for calculation of these things. But we simulated these things in normal traditional programming environment. So and use 12 data sets to compare how it comes out. There are some of the quantum gates equations are there, but I'm not going details into the quantum mechanism. It is, and I should use the, just a minute. Actually, I converted this file, the PDF file, to PPT file, but that equations are got jumbled up. So I am trying to find the original files. I think I should explain from here. So how the superposition of actually qubit is represented by this equation, because it is not one binary bit, 2 bits, 0, 1. 0, 1 is superposed. So the representation mechanism in quantum computing is like this. And quantum gate, we used Hadamard gate and quantum rotation gate. The equations are like this. This is some calculation we did with these equations. And we used also measurement. So for measurement also we use these quantum methodologies. So the owls are actually, this is the flow chart of the flow diagram of this quantum based, quantum inspired feature subset selection algorithm, where initially the populations, binary owls, the populations has 0 values and 1 values. We transform these population to quantum owl population by using Hadamard gate. So Hadamard gate transforms that in, they can superimpose in 0, 1 stage. So there should be, the qubits should be lesser than what we used in binary bit. So the what should I say? That bit space is more compressed. In that way, our computation is lesser. And then this binary quantum population, we calculate the fitness. Fitness value is calculated by rotation gates, and we update the gate, and then we measure, and we have the new quantum owl population. If we meet the stopping condition, we'll stop, or if we don't, if we need more iterations, we'll again go to that population. We will measure, and if after measurement we will get the normal values, we calculate the fitness value, and then for the fitness evaluation, we use the rotation gate. We update the positions of the owl, and then new population is generated. And again, we actually do this iteration. And finally, after the stopping condition is met, we'll actually find the best owl position. The main thing is that our calculation of this initial population, that fitness, and the updation, mainly the updation, we used some of the gates. And those gates have some mathematical equations. So we just implemented those mathematics in programming so that we can calculate using those gates. And our equation of this measurement rotation value calculation accordingly has changed to these equations. Update mechanism. And this is the algorithm here. So we used some data sets, but these are the descriptions of the data set. But here we actually used, for the fitness function, we use the classification accuracy. And we get this quantum inspired. This is the result for our quantum inspired algorithm, our previous algorithm, and some other algorithms, meta heuristic based algorithm. And we find that this quantum inspired algorithm is not bad. But here we have that in terms of average computational time. But what do we feel that if the dimension is high, it took lots of computation and computational time was quite high. This work we presented in this conference, and then our next work was actually here we found that this time is quite high. Implementing those gates in traditional computational platform, not in the quantum computing platform. So we just implemented those equations in the platform. That took quite a lot of time. So we tried, when you tried for the high dimensional data sets, especially in microarray gene data set for feature subset selection, we found that it takes a lot of time. So here for high dimensional data sets, we modified those algorithms in 2 steps. One thing we modified is initially we used some ranking based methods. So from initial high dimension, we reduced the dimension to a lower dimension first by using some ensemble of ranking based methods. And in the second stage, we used this quantum inspired owl search algorithm because in our previous experiment with this quantum inspired owl search algorithm, we noticed that classification accuracy is very good, but it was taking longer time. So we used here not the wrapper based, but filter based. So whatever filter function we used for ranking, we used some of the filter functions for in the second stage also for filter based subset selection. And also we compared with the same some 25 microarray data set. We tested this our algorithm and compared with our previous this quantum inspired owl search algorithm, wrapper based algorithm, and different other beta heuristic based algorithms. So here actually the main idea was we introduced 2 steps to reduce the high dimension to first the lowest dimension with only feature ranking. And we didn't use only one filter ranking methods, but we used different ranking methods, and then we took an ensemble of those ranking methods to select the first some portion of the dimension. And then we used in the second step, we used this quantum inspired search algorithm with filter function, with the filter fitness function to find out the final feature subset. So, so again, the same thing, the equations are a bit distorted in the PPT file. But the thing is that the same thing we did, we represented the owls in quantum formulation, and the measurements we use some gate. For update equation, we use some gate. And the whole process we actually calculated in with some concepts from quantum theory, and we implemented those equations in our algorithm. And the results we get, these are the data sets, 25 data sets. And results were actually accuracy wise, it was not, it couldn't beat the wrapper based algorithm. In fact, almost same, but computational time was quite low for this because we reduced the time also, reduced the dimension also. And so in the reduced dimension, the computational time was lower. And of course, the final number of features in the subsets are also low. So this was some of the comparison with other methods in other papers, because we did this to write our paper. So our proposed algorithm was comparable with, and in some cases it is better. So we actually this paper is now accepted in a journal. So yeah, so we had to do this comparison to prove that our algorithm is not bad for some of the data sets, some of the data sets, and this is also accepted. Now, in the finally, we changed our. This is a new algorithm which actually is not based on owl search. We tried to design a algorithm based on quantum procedures only. So quantum optimization problem, one thing is that any optimization problem, if you can transform it into QUBO form, then QUBO is quadratic unconstant binary optimization form. If you convert to this form, it can be solved on a quantum computer based on quantum annealing process. So, but these quantum computers are not available. We actually converted our problems into feature subset selection problems into QUBO problems so that it can be solved using a quantum computer. But at the time being, as we don't have access to any quantum computer, we used some simulator, that is annealing based simulator. And within the simulator, quantum annealing simulator we used. So in the simulator, it was shown that if we can prove that it is it gives a very good performance if the number of features is small. But if the number of features is increased, what happens? The computation is increasing very much. And in fact, the simulator, we could not experiment with high dimensional data. We only could experiment with low dimensional data. And for low dimensional data, it was seen that it was very much experimental, but we could find that this method gives quite a good performance in terms of classification accuracy. So what we did is that we generated that QUBO model for all the filter functions. It was based on filter best feature selection algorithm, and then we generated the QUBO model and then run on the simulated quantum annealer and output the result. So this is the actual we use this solver, SQAD solver, and we found the results. We used 3 types of ranking methods. One is a popular minimum redundancy, maximum relevance, MRMR method for feature subset ranking, and joint mutual information correlation-based filter. So these 3 filter functions, we converted it to QUBO function. So just a QUBO matrix we could find out, and then calculated this QUBO matrix over simulator. And the result I can show. We used this type of data set, these data sets, where the number of features are not much, it is the one number of features. And the one thing we noticed that compared to classical simulated annealing or any other classical feature selection method, this quantum-based feature selection method is more stable, because in classical feature selection method, suppose if we find in this slide, I do not know whether it is feasible for any data set. If we run the program different times, the different features come out to be the good feature subset. That is, the features are not stable. So if we repeat the experiment, the same result we are not getting for classical methods, but for simulated quantum annealer, while we use the quantum-based method, this is quite stable. All the time we run the experiment, we run 100 times in fact, but all the time the same features came out to be the best feature subset. So that is one good point, and the classification accuracy was also better than other classical methods. But one problem is that we couldn't use very high dimensional data, because then the computation we couldn't finish in the simulator. So if someday the quantum computer is available, then we think that these quantum-based methods will give better performance. So this is the paper also we submitted, and it was published in the references here. It is published in 2021. So this is what I want to say in this today's talk. So thank you, and of course I will discuss anything if you want to know anything, any question, any comment, or anything to be discussed in detail. I'll be happy to do that. Thank you very much. So any comment, anything, any question? Because I can't understand if it is visible, or if you interact with me, I will give you more input. So any question? I completed.
Thank you, Professor Bosky, Madam. On behalf of management and the Department of Computer Science Engineering, I'm giving my warm thanks to you for this wonderful session in 1 week FDP program about recent tools and technologies using for the data science and artificial intelligence, Madam.
Thank you very much. So if you have any question, I can discuss, but I don't know whether I'm audible or visible, because this type of interaction I'm not very much comfortable with, this online interaction.
This all introduction, this all complete session, it is for recorded, Madam. It is visible only.
Okay.
Your screen is visible, and then your audio is also very good only, Madam.
Okay, thank you. And later also, if any participant contact me, or if they want to know anything, I'll be happy to discuss.
Okay. Dear participants, if you want to ask any questions, Madam is available now. You can ask any kind of questions here regarding to this session. Madam is ready to answer here. Okay. Okay, Madam.
Okay.
We can wind up the session, Madam. Thank you.
Okay. Thank you.
Thank you. Thank you, Madam. Thank you, participants, for attending this wonderful FD.